Hello and welcome back to Introductory Astronomy. Today we're going to talk about the early universe, and we begin this chapter by a picture that's taken underground on the Swiss-French border near Geneva. And what you can see there is technicians that are using the world's biggest physics experiment to explore matter more deeply than ever before. This experiment is called the Large Hadron Collider, and it simulates events that occurred within the first second after the origin of the universe by violently smashing together subatomic protons. Scientists are now testing their best theoretical ideas about how the universe began against the data created in this machine. So in this chapter, we're going to talk about what were the conditions during this first few seconds of the universe, and how did these conditions change to give rise to the universe that we actually see today. By studying the earliest moments of our universe, we enter a truly strange and alien domain. As we move backward in time towards the Big Bang, our customary landmarks slip away one by one. Atoms vanish, then nuclei, and then even the elementary particles themselves. In the beginning, the universe consisted of pure energy at unimaginably high temperatures. As it expanded and cooled, this ancient energy gave rise to the particles that make up everything we see around us today. Modern physics has now arrived at the point where it can reach back almost to the instant of the Big Bang itself, which allows scientists to unravel some of the mysteries of our beginnings in time. The total energy of the universe consists of both radiation and matter. As the universe expanded, the number of both matter particles and photons per unit volume decreased, but the photons were also reduced in energy by the cosmological redshift, in turn reducing their equivalent mass and hence their density even further. As a result, the density of radiation fell faster than the density of matter as the universe grew. Thus, radiation dominated matter at early times before the crossover point. As the universe cooled, it went from being radiation-dominated to being matter-dominated. And dark energy becomes more important as the universe expands. In the very early universe, one of the most important processes was pair production. These diagrams show how two gamma rays can unite to make an electron-positron pair and vice versa. So let's take a look at frame A. Two photons can produce a particle-antiparticle pair, in this case an electron and a positron, if their total energy exceeds the mass energy of the particles produced. And in frame B, the reverse process is particle-antiparticle annihilation, in which an electron and a positron destroy each other, vanishing in a flash of gamma rays. Frame C is a picture from a particle detector. A particle detector is an instrument designed to show the tracks of otherwise invisible subatomic particles, which helps us visualize pair production. A gamma ray, whose path is invisible because it is electrically neutral, arrives from the left, dislodging an atomic electron and sending it flying, so you can see the longest path. At the same time, the gamma ray provides the energy to produce an electron-positron pair, which are the spiral paths, which curve in opposite directions in the detector's magnetic field because of their opposite electric charges. The V-shaped tracks at the very right are the result of a separate particle interaction. In the very early universe, the pair production and recombination processes were in equilibrium. When the temperature had decreased to about 1 billion Kelvin, the photons no longer had enough energy for pair production and were quote-unquote frozen out. We now see these photons as the cosmic background radiation. In frame A, we see at 10 billion Kelvin, most photons have enough energy to create particle-antiparticle pairs, so these particles exist in great numbers in equilibrium with the radiation. Remember that the label E- refers to the electrons and E+ to positrons. In frame B, we have about 1 billion Kelvin. At that point, photons have too little energy for pair production to occur, so electrons and positrons are no longer in thermal equilibrium with the background radiation field. This figure here illustrates the main events at the different epochs of the universe. So it is some kind of cosmic history plot. The average temperature and average density throughout the history of the universe is shown here clearly, and some key events are marked and discussed in detail in the text. Notice how we start with the radiation era, moving on to the matter era, and finally the dark energy era. Here's a little bit about a current understanding of the forces between elementary particles. The way we understand forces nowadays is by using the idea of a third particle called the exchange particle. Different forces freeze out when the energy of the universe becomes too low for the exchange particle to be formed through pair production. So how does that actually work? Here we have a standard diagram of fundamental forces. Forces between elementary particles are believed to be transmitted through the exchange of other particles called bosons. As two particles interact, they exchange bosons, a little like playing catch with a submicroscopic ball. And as the universe is becoming cooler and cooler, different forces were frozen out, and the universe was too cool for the exchange particle to be formed through this pair production. So if we use all these ideas and extrapolate the Big Bang back to the beginning, it yields what we call a singularity, a quote-unquote point of infinite density and temperature. Now, this may or may not be accurate. We can only understand what happens back to about 10 to the minus 43 seconds after the Big Bang. Before that, we need physics of which we know very little at the moment. Therefore, we cannot predict anything about what happened before the Big Bang. Indeed, the question may be meaningless. The Big Bang represented the beginning of the entire universe. Mass, energy, space, and time came into being at that instant. Without time itself, the notion of before does not exist. Consequently, some cosmologists maintain that asking what happened before the Big Bang is a little like asking what lies north of the North Pole. Others, however, disagree, arguing that when the correct theory of quantum gravity, or the theory of everything that will unify gravity and quantum mechanics, is constructed, it will remove the singularity and allow us to address the question of what came before. These first 10 to the minus 43 seconds after the Big Bang are called the Planck era. At the end of that era, the gravitational force freezes out from all the others. The next era is called the GUT, the Grand Unified Theory era. Here, the strong nuclear force, the weak nuclear force, and electromagnetism are all unified. The next era after that is called the Quark era. During this era, all the elementary particles were in equilibrium with radiation. After about 10 to the minus 4 seconds after the Big Bang, the universe had cooled enough that photons could no longer produce the heavier elementary particles. The only ones still in equilibrium were electrons, positrons, muons, and neutrinos, which is why this is called the lepton era. About 1 second after the Big Bang, the universe became transparent to neutrinos. After 100 seconds, photons became too low in energy for electron-positron pair creation, which marks the end of the radiation era. The next major era occurs when photons no longer are able to ionize atoms as soon as they form. This allows the formation of hydrogen and helium atoms, which can then form larger structures. For the next 3 billion years, galaxies and quasars begin to form. After that, they start to merge. Galaxies evolve into the ones we see now, and star formation goes through many generations. Table 27.1 lists the 4 fundamental forces and the particles on which they act. There are 6 types of quarks, up, down, charm, strange, and top, bottom, and 6 types of leptons, electron, muon, tau, and electron, neutrino, muon, neutrino, and tau, neutrino. All matter is made of quarks and leptons. And remember, all matter only comprises 4% of the universe. Your book goes in great detail on the fundamental forces, in more precisely 27.1. I'd like to say just a few things. For example, the theories of the weak and electromagnetic forces have been successfully unified in what we call the electroweak theory, which was shown in the table in the previous slide. At a temperature of 10 to the 15 Kelvin, these forces should have equal strength. There's also a lot of work that was done in unifying the strong and electroweak theories, which we believe would have equal strength at a temperature of 10 to the 28 Kelvin. One of the many predictions of this series is the prediction of supersymmetry, the idea that every known particle has a supersymmetric partner. Now, we have not been able to unify the 3 forces with the last force, the force of gravity. One theory that showed early promise is the string theory, the idea that elementary particles are oscillations of little loops of string rather than being point particles. This idea avoids the unphysical results that arise when point particles interact. However, string theory still is a work in progress, and at the moment of this lecture, there is no satisfactory theory that unites all 4 forces. Let's talk a little bit about the formation of nuclei and atoms in the early universe. As you can imagine, hydrogen will be the first atomic nucleus to be formed, as it is just made up of a proton and an electron. Beyond that, helium can form through fusion. So we have a 3-step fusion process right there, which I don't want you to confuse with the fusion process that takes place in stars. Now, note it is not the same, and I will show that in the next slide. Here we have the reaction sequences that led to the formation of helium in the early universe. A deuteron is a nucleus of deuterium, which is the heavy form of hydrogen, hydrogen 2. Let's compare that to figure 1627, which depicts the proton-proton chain in the Sun, which is coming up in the next slide here. Here we are. Solar fusion. In the proton-proton chain, we have a total of 6 protons and 2 electrons that are converted into 2 protons, 1 helium-4 nucleus, and 2 neutrinos. The 2 leftover protons are available as fuel for new proton-proton reactions, so the net effect is that 4 protons are fused to form 1 helium-4 nucleus. And of course, energy in the form of gamma rays is produced at each stage. Note how this process is different than the helium fusion process in the beginning of the universe. Now, this helium fusion process would lead one to expect that 1/4 of the atoms in the universe would be helium, which is consistent with observation, keeping in mind that nucleosynthesis is ongoing in stellar cores, so those numbers are slightly different. Now, you might wonder why fusion did not continue in the early universe to create heavier and heavier elements, just as it does in the cores of stars. But that did not happen. In stars, the density and the temperature both increase slowly with time, allowing more and more massive nuclei to form. But in the early universe, exactly the opposite was true. The temperature and density were both decreasing rapidly, making conditions less and less favorable for fusion as time went on. So even before the supply of neutrons was completely used up, the nuclear reactions had effectively ceased. Most deuterium fused into helium as soon as it was formed, but some did not. Deuterium itself is not formed in stars, so any deuterium we do see today must be primordial. This gives us a very sensitive way to estimate the present-day matter density of the universe. Here we have a deuterium abundance plot. The present-day abundance of deuterium depends strongly on the amount of matter present at early times, and this in turn determines the present-day density of the universe. So measuring the amount of deuterium in the universe gives us an estimate of the overall density of matter. The best deuterium measurements are marked on this plot. They imply that the density of matter in the universe is at most a few % of the critical value, just like we were seeing before. Now, the time during which nuclei and electrons combine to form atoms is referred to as the decoupling epoch. This is when the cosmic background radiation originated. When atoms formed, the universe became virtually transparent to radiation. Thus, observations of the cosmic background radiation allow us to study conditions in the universe around a time when the redshift was 1100 and the temperature had dropped below about 3000 Kelvin. For an explanation of how we can see a region of space, 14,000 megaparsecs, or 46 billion light years away, when the universe is just 14 billion years old, please refer to your textbook in more precisely 24.1. Study chapter sections 27.1 through 27.3 and be able to describe the characteristics of the universe after its birth and how matter has emerged. Be able to explain how and when the simplest nuclei have formed.